I'll make it pretty clear. Let me see what I have here.
I push the button.
Okay. Thank you very much. Welcome everybody to the May 20th edition of the San Antonio Cloud Computing Group Meetup, virtual as it has been. I'd like to thank everyone from the San Antonio Cloud Computing Group, everyone from the .NET Virtual User Group for being here. And I'd like to thank Dave and the .NET Foundation for hosting and running this thing. I appreciate the great work they do in running and hosting these things, as well as their great work educating, advocating, and kind of bringing in the new generation of developers. I'll post that link in the chat here in a moment. We have one announcement. 1 week from today, on the 27th, our next meetup event will have Mike Bankovich, who is a former Microsoft developer tools and cloud evangelist who has spent his career helping developers and enterprises explore and apply new technologies to solving information challenges. He'll be here and he'll tell us about the permit to cloud, which is how to migrate your app and land with confidence in Azure. I don't have a link for that one yet, but I'll post that to our page as soon as I do. And now to our main event of the evening. I'd like to introduce our guest, Mark Brown. Mark is a principal product manager for Azure Cosmos DB, and I'll let him intro his talk since he knows all about it. But I'm very excited because I don't know how often it is we get to hear firsthand, from the source material. So thank you for being here, Mark, and I'll hand it over to you.
Thank you, Kellen. I've known Mike Bankovich for, well over a decade probably. So he's a great guy. Good to have him on next, was it month? You guys meet monthly?
No, we've been, it kind of depends on the guest availability. We try to meet twice a month. So on Thursday nights around this time.
Great. All right. Well, thanks for having me and welcome everyone. My name is Mark Brown. I'm a principal program manager on the Cosmos DB team. I've been on the Cosmos DB team for probably, I guess, a little over 3 years or around 3 years. Prior to that, I was on the Azure networking team. And prior to that, took a little time off and worked on the Azure web apps and Redis cache. I've been in Azure since about 2011, I think, and I've been at Microsoft now just about 20 years, all told. So quite a long time, worked on lots of different products and services. I have to say, this is probably the most fun I've had. NoSQL distributed databases is a heck of a lot of fun. Lots of good tech in here. My day job for Cosmos is twofold. I'm the program manager for what's called our resource provider. That's basically our control plane backend. So when you provision an account using, say, an ARM template or a PowerShell or a CLI or even REST, all that API stuff, the management API is what I PM. And then I also run a team of other PMs as well. And we're just basically trying to help spread love and awareness around Cosmos DB. So today I'm going to talk about data modeling and partitioning in Cosmos DB. This is probably, I would say, the most important topic for anyone new to this type of database to understand. So let me kind of go through objectives here. First, I want you to get familiar kind of with Cosmos DB's core concepts and kind of our API in there, and understanding data modeling best practices. And then we're going to apply that to a real world scenario here today. And then I'll help you understand throughout all this kind of how Cosmos differs from a relational database when designing a data model, because we're going to start with a relational data model. So what is Azure Cosmos DB? Well, it's officially Microsoft's NoSQL database on Azure. When we say NoSQL, what we really mean is Cosmos DB is both non-relational and horizontally scalable. So let's talk about the horizontal scale aspects of Cosmos DB. Unless your workload is small with just a low amount of data or request, your data is likely going to be stored on a bunch of different physical servers or partitions within something we call a container. Now in Cosmos, we abstract all this away, but under the hood, you're reading and writing data in and out of Cosmos across this cluster of servers. And this is better known as scale out, and it's how we achieve horizontal scalability, enabling both unlimited storage So when you need more storage, we just simply add more servers to your cluster. This also provides unlimited throughput because each of these computers has its own CPU, memory, and I/O running through it. So adds additional capacity to handle the request when you need it. Now, Cosmos DB is also non-relational. So when working with relational databases, you have the ability to do things like define constraints between the different entities you're storing. This lets you do things like create foreign keys, perform join operations, those types of things. Non-relational databases like Cosmos DB don't implement any of these relational constraints. And the reason why is because Cosmos is a horizontally scalable database, and your data is likely going to be spread across multiple servers. This could be tens or even hundreds of servers, depending on the storage or throughput needs you have. Now, I don't want to suggest that it's not technically possible to enforce relational constraints across a cluster of servers, but doing so would actually have an enormous impact on the performance and availability for your database. And because Cosmos is designed to provide predictable performance, we don't really provide a way to declare these types of relational constraints. So you may be asking yourself, well, is Cosmos okay to use for relational workloads? And definitely, it most fact is. And in fact, most workloads on Cosmos are relational in nature. You just need to use and learn different techniques to implement the relationships between your entities. And this approach is very different than designing a data model for a relational database. For those that are new to this type of database, you should not follow your intuitions. Best practices in the relational world don't translate very well to this type of database and may even be anti-patterns. Okay, so let's put this into practice. I'm going to spend the rest of this session taking a relational database that anyone who's familiar with SQL Server should know, the AdventureWorks 2017 database. Well, actually, we'll just take a small part of it. These tables represent the canonical e-commerce workload, if you will. We've got customers with the customer table, customer address, and customer password. For the products, we've got, of course, the product table, and then there's your product categories and product tags. And then finally, we have our sales orders. So we've got our sales order header here, and then also our sales order detail. So with a non-relational, or excuse me, yes, with a non-relational document database like Cosmos DB, there's not much we can do with the tables the way they are. You would never use these tables as is because the cost of performance for trying to do operations on them would be prohibitive. Another thing I want to point out too is that in a relational database, the relationships between the data are important for modeling the database. For a NoSQL database, this is only part of the story. What's most important when designing a data model for a NoSQL database is to look at the access patterns for your application. How does your app read and write data out of your database? And as I'll show you through this talk, we're going to look at the application patterns and use that to inform the design and the decisions we're going to make in terms of modeling this database. Okay, so a real-world e-commerce platform would obviously need to implement a lot more functions than this. But this subset really is enough to kind of guide and illustrate the different design techniques that we want to showcase. So here's what our little mini e-commerce site is going to do. We're going to create and edit a customer, and then we want to retrieve a customer. We want to create and edit product categories, and then we want to list all product categories. And then we'll do the same for product tags. So we'll create, edit, and list those. We want to create a product and edit a product. And then we want to list all products from a category. And we also want to include the name of the category and the tags in there. Because if you look here in product, we don't have the category name in here, and then the tags is sitting in a completely different set of tables with a many-to-many relationship. So we want a query that's going to provide all of that. We also need to create a sales order, and then we want to list all sales for a customer. Okay, so that's a different one. And then we have another one, which we want to query top 10 customers by the number of sales orders they have. So this is kind of like a light analytics scenario, if you will. Maybe I want to send out a nice gift to them, or I don't know, a coupon or whatever, saying, thanks for being a customer. Here's a little something for you. Okay, so let's get started remodeling this relational database in Cosmos DB. And we'll start here with the customer entities. So we have three tables here. I've got customer, customer address, and customer password. And first, what we need to do is we need to translate these into its corresponding JSON document. Now, we could keep these in separate containers in Cosmos, but let's look at the operations we need to support. That includes both creating a customer and editing a customer. Now, given that Cosmos DB stores data as JSON, another approach we could take is to embed the address and the password tables into our customer table. Now, when I create a new customer, I only need to insert the data into a single container. Reading data is also easier because I only need to read from a single container as well. So both these operations would now be faster and less expensive to execute because I've embedded them into a single container here. So at this point, people often ask, when would you embed data versus reference it within a database like Cosmos? There's actually some good rules of thumb on when you would do these types of things with a JSON database like Cosmos, where you can have hierarchical data like this. Generally, you want to embed data or entities together when there's a one-to-one relationship for the data. So for customer and customer password, you would have that one-to-one relationship. So that makes a good candidate for that. Or if you have what we call one-to-few relationships. Now, this is different than one-to-many. One-to-few is actually a little more precise in that it explains or helps to codify, is it an unbounded relationship in that sense, right? So if you have one-to-few, they're just a handful of things. It's typically some kind of bounded amount. This would be like address, right? Like address is strictly a one-to-many relationship to a customer, but you don't have an unlimited number of addresses, or you don't have an insane number of addresses. You just have a small number, like maybe one or two. You got yourself, your wife, your kids, or your mom, or your dad, or whoever. But so it's a one-to-few relationship that we like to call. And then the other aspect is that the related items are queried or updated together. Is another reason why you would want to embed a reference within there. Now, you want to reference, should be embed. Now, you want to reference when the relationship is one-to-many, and especially if it's unbounded. And I'll explain why that's important in a little bit. Also, if you have a many-to-many relationship, you also need to reference this data rather than embed it. And then also, if the related items are queried or updated independently, also another good option for referencing the data within a database like Cosmos. Okay, so because we have this one-to-one and one-to-few relationship between our entities, and because we usually retrieve all the data for a customer at once, it makes sense to embed everything inside this single JSON document here. Now that we've defined our first entity, we need to store our data, customer data, into a container, and we'll call that customer. Now, when creating a new container, we also have to define its partition key within Cosmos DB. And you may be asking, well, what's a partition key? Well, remember earlier I said that Cosmos DB is basically Cosmos DB container is an abstraction over a cluster of physical servers. When storing documents in a Cosmos DB container, these documents end up getting dispatched to different physical servers. So the question is, how do I decide that this document should go there and that document should go there? Now, technically, we're not directly assigning documents to servers. Instead, documents are being written to what we call logical partitions. And it's these logical partitions that sit on different physical servers. And so from a user's perspective, you don't really need to care about physical servers when designing your data model, just that your data gets written to these different logical partitions. So again, now how do you got to ask, like, how am I going to decide which logical partition a data should go on? Well, that's where the partition key comes in. So when creating a new Cosmos DB container, you define the container's partition key, which is the name of a property that Cosmos will use to decide which logical partition your data should go to. Think of it as like an address to route your data to within your database. Now, using the example of a container partitioned by username, we would end up with a logical partition where data where username equals Andrew is on one partition, and then you have a second logical partition where data where username equals Deborah is assigned to, and so on. Now, there's two constraints to keep in mind when designing a data model on Cosmos DB. First is each document has a maximum size of 2 megabytes. Now, remember before when I talked about when to embed or when to reference, it's because each document can be no larger than 2 megabytes, which is why you don't want unbounded arrays inside your documents. Another restriction too is each logical partition has a maximum size of 20 gigabytes. So you can't have more than 20 gigabytes of documents where, say, username equals Andrew. And when working with data, what we want to achieve, or strive to achieve at least, is an even distribution of data across our different logical partitions. So if one partition gets a lot more data stored on another, this is what we call a hot partition, and we want to try to avoid that. Same goes for requests as well. If most or all of your requests hit the same logical partition, this is going to be a bottleneck that's going to drastically limit the overall scalability of your model within there. What we want to end up with is a design where storage and throughput are more or less evenly distributed across our different logical partitions. So partition key plays an important role in both the performance and scalability for your database. Let's take that example again of a container partition by username. Now, if we were to issue this query, you'll notice that it filters on the username property, which thankfully is our partition key. And because Cosmos DB understands that, it's going to send this query to a single logical or physical partition. That means this query is always going to hit one physical server. So its performance is always going to be really good. Now, if our query is filtered on something else, say like favorite color here, we would have no idea where the results are. So in this case, Cosmos fans out the query to each and every logical partition and thus every physical partition. And as you've probably already guessed, this is going to hit every physical server. And this is what we call a cross-partition or fan-out query. And more specifically, as a fan-out, means it's going to hit every single physical partition in your database. Now, such a query will work, but it does have an impact on latency, throughput cost, and ultimately scalability. Now, whoops, sorry, I need to go back. Now, for small containers, this performance impact is not that bad. In fact, for a container with just a single physical partition, you won't notice any impact in the performance at all. However, as your database grows larger, the impact becomes worse and worse as you have to hit more physical servers to answer your query. And this is the scenario that precisely traps so many people new to this type of database. Is typically developers will do dev and test on a small data set and then conclude that their design is good because the performance they measured was acceptable. In a NoSQL database, you don't truly know if your design is scalable until you actually measure it under heavy load or you have a good amount of data in there about the concurrency of your operations. Okay, now with all that knowledge about partitioning, how do we choose the right partition key for our customers? Remember before I showed the operations we need to do for our customers. We had three things we needed to do. We needed to create a customer, we have to edit a customer, and we also need to retrieve a customer. In this case, we're going to retrieve them by their ID. So ID of the JSON documents we're going to store in this container should make for a pretty suitable partition key. Keep in mind, too, the other thing that's important is the concurrency of these operations. We're not often creating or editing a customer, but we are retrieving them quite often, right? Every time they log into the e-commerce application, we need to look them up. So this is why you want to optimize around, well, certainly the operations that are going to be run, but also the frequency and concurrency of those operations as well. Plays a huge part. Okay, so the ID of the JSON documents is going to make for a suitable partition key here. Note that when using the ID as the partition key, we end up with as many logical partitions as there are documents in the container, with each partition containing only a single document. And that's perfectly fine. Many users are concerned about this, having this high number of logical partitions, but there's no need to worry. Logical partitions are a virtual concept. So Cosmos co-locates logical partitions on the same physical servers and then moves them to different physical servers when needed. And there's no upper limit to how many logical partitions you could have in a container. In fact, functionally, a single document per logical partition is a key value store in Cosmos DB. And you can have key value stores basically infinite size in Cosmos, an infinite number of logical partitions. Okay, so let's do a demo or two here. In this demo, I'm just going to show you how to query for a customer by ID and then return that customer's data. And I'll show you some code here as well. So I've got a little demo app all set up here. And we're going to run this one, query customer right here. So let me open that up. And here you can see I'm getting a reference to my database and my container. I'm going to look up this customer ID. So this is the ID of the customer I'm going to get in there. I've got a SQL statement. So we're using Cosmos DB's SQL API which has a very SQL-like syntax. It's not ANSI SQL. Keep in mind, we're a JSON store. So our flavor of SQL is meant to work with JSON, not with fixed columnar data like you'd find in like a SQL or any Postgres or anything. Okay, so next, then I'm going to create what's called a query get item query iterator, and I'm going to pass in my new SQL definition there, and then I'm going to pass in a parameter, and then I'm going to create some request options here, and then I'm going to specify my partition key. Now, for Cosmos DB, you can do one of two things. You can you don't have to do this, but if you pass in the value of the partition key in the where clause, it will kind of suss it out and then use that to route the query. However, I'm calling it out here because it's kind of a best practice to put this in the request options. And this functionally is what is going to route the query to the correct physical partition in your database, so it knows where to go find that data. So that's my query definition here. And then I'm just going to put this in a while loop and then loop through the results here and call read next async. That's going to fetch the first record. And then just print out my customer using a handy little print function with a Newtonsoft library there. And that's it. Just loop through all. There's only one customer, but I'm still going to put this in a for each just to show that that function there. Okay, so over here in my app, I've got my apps right here, and I'm going to run menu item A, and I'm going to query for a single customer. This will take a second because it's just starting the app. It hasn't connected to the database yet. There we go. Okay, so there's our customer record. You can see there's the original customer data there, the title, first name, last name, email address, phone number, and creation date. Here's address in an array. Now there's only one address in here, but there it is. And then here's the password object that we had in our other table. And here you can see I returned the request charge of 2.83. Now this may be new to you as well, but Cosmos DB uses what we call request units per second, or RUs. This is how you measure throughput in Cosmos DB. And it's essentially a proxy for compute and IO and memory within there. So when you provision a new container in Cosmos, you have to specify some level of throughput. And the more throughput you provision, the more compute power you get, the more you can do, the more operations you can handle, the more you can do. You also get more storage with that because there's an implied level of storage for a certain amount of throughput within there. So knowing how much your operations cost is a way to figure out, okay, I'm going to run this operation 10 times a second. I know it costs 2.83 RU. I'm going to, and then add that up with other operations that I know I'm going to run at some level of concurrency, add all those up to figure out how much, just roughly, how much RU I need to provision total for my database. Another thing I'll point out too is because throughput here is measured or governed per second, the longer you can amortize request over time, the lower overall throughput you need. I often hear from customers like, I want to run a batch job that's going to do a whole bunch of work, and I've got to provision an insane amount of throughput to do it. Why is it so much to do that? And usually my answer is, can you stream the data rather than batch it? Because if you can stream it, you can process it over a longer period of time. That's going to require less throughput, and you're going to pay less for it. So anyway, that's just talking about throughput, something to know there. But we want to measure that here. So that's 2.83 for that request, to that query. Now, another thing I want to show you is if you're doing a query where you're passing the partition, the partition key and the ID for the data, you can do something that we call a point read. And it's part of the non-query operations for, say, inserting, updating, deleting, and reading. And let me show you that. So here I have a function called getCustomer, and get my database and my container, same customer ID. And I'm going to use this function here, which is called read item async. And I'm going to pass it precisely two things. I'm going to pass it the ID for the data I'm looking for, in this case, customer ID, and the partition key, which is the same. In this case, it's customer ID. So I'm going to go and get the same amount of data using a point read And let's see how that runs. So I'll run number B, and there it is back. And look here at the bottom, the request charge for this was just a single RU. And this is something we guarantee for any point read operation that you make for a kilobyte of data or less is always going to cost you a single RU. And the reason is because this goes straight to our backend. We know the cost for a kilobyte of data, and so that's why we can guarantee it at a single RU. It's going to be much faster, much cheaper. So if you have a lot of high concurrency reads, if you can structure your data or model your data and partition it such that you can fetch those single items with a partition key and an ID, that's what you should do, because it's going to give you the best performance, the best bang for buck for your application. Okay, let's go back to slides here. Are there questions I get through this, Kellen, or just people just hang out and then do it at the end?
Yeah, if anybody wants to ask any questions, that's pretty good. We only had one question that had to do with kind of the stream. If he was asking if there was a way to up the size of the text in your editor there. It seemed like, or the quality of the stream. But yeah, I'm monitoring for questions. So
I am going at here. I can make this bigger. Hold on. Yeah, it's funny. I host a podcast, and I'm always telling when I do checks, I'm like, you gotta make your stuff bigger. We'll make this bigger. And whoops, where'd you go? And then let me zoom up Visual Studio here, and we'll get that to like say 120 maybe. How's that look? That should be better.
Yeah, that's
right.
better to me.
Cool. All right. Yeah, thank you, folks. Sorry for running small text here. Make it better. I'm going at 1080p right now, so I can't go any higher. Okay, so that was our query customer demo. Let's move on to products, and we'll look at the product tables next. First up is the product category table. So we're going to do the same thing we did earlier, which is translating this into a JSON document. And we need to store that document in a container. We'll call that product category. And then next we need to figure out its partition key here. So again, we need to look at the requests that we need to support in our app, right? So here we need to create a product category, edit a product category. And then I want to list all product categories. And again, I want to point out when you're looking at the operations you need to support, it's important to know the volume of those operations. For instance, we probably aren't creating or editing product categories very often. But just like with customer, we need to list the query product categories quite frequently within our e-commerce application. But there's a problem we've got here. There's no where filter on this query. So how do I make this thing a single partition query? Well, again, we're going to, whoops, where are we? Okay, so what we're going to do is we're going to use a little trick here. And I'm going to create a new property and give it a constant value in our document. So here I've created a property called type, and I've given it a value of category. Now I can partition this, this container by type, and then just set this value of category in every document. Now, look, I know this looks a bit weird, but it actually makes sense if you just stick with me. I'm going to iterate on this design through the rest of my talk here, and you'll see how this actually makes a whole lot of sense, and is actually a really smart thing to do. So, okay, let's do a demo here. In this demo, I'm going to show you a query for product categories, and then we'll measure the RU charge in our app. So back to my app here, I'm going to query product category, query products by category ID. Sorry, is that the thing I'm doing? I'm listing all product categories for my one. This is the one I'm going to run. Okay, so this should look familiar. I'm going to get here, let me scroll this thing out of the way. Yeah, that's okay. So top of this looks just like the same for the others. I got my database, my container, my query. And here you're going to see it's just basically hard coded. So select star from C, where C type equals category. And then I'm going to create my query iterator here, pass in the partition key. Guess what? Hard coded category. And then iterate through the results here. And I'm just going to print these out. And I'm going to print out the request charge. So let's list all product categories here. That's option C. And here you can see a bunch of product categories. I think there's 37 in this database. And there's my query request charge, 4.04. So not bad. That's a pretty good cost there, just for you to run that query. So in a real world scenario, it's not like you would run this query every time, right? You would run this at startup and then cache it in memory or something, right? So you wouldn't worry too much about the cost of this query, but certainly you wouldn't want to be running it over and over and over again because it's the same data and it doesn't ever change. All right, let me go back to slides here. Okay, so next we're going to look at the product tags here, and I'm going to translate that into, of course, its JSON document format here, and we'll store it in its own container. We'll call that product tag. Pretty unique. Now, it turns out tags shares the exact same access pattern as categories does. So we're just going to apply the same strategy here. I'm going to add a new property called type, and I'm going to give it a value of tag and then stick that for each document. All right, next, moving on to the product table here. Going to translate into its JSON. And next, I want to look at the relationship from product to product tags. Our product table here has a many-to-many relationship with product tags. And I need to access the product tags in my application, meaning when I display a product, I need to display the tags for it as well. I also would want to query for a product using its tags as well in here. Now, I could do this in one of two ways. I could store the product info in the product tags table, or I could materialize tags in my product table. Now, given that there's much fewer tags per product than product per tags, it makes sense to materialize product tags and embed them in my product table, right? Because that's going to be a bounded array. You're not going to have 1 million product tags for a product, or hopefully you won't. So remember, with that one-to-few relationship, it's a good candidate for embedding tags into my product table here. And then next, we're going to store products in its own container. We'll call that product. And then next, now we need to figure out a good partition key. So again, we're going to look at the operations here and decide on partition key. We, of course, need to create and edit a product. But the interesting operation here is querying for a product by category. Because this is likely, at least in our design, how customers are going to search for products, or at least one primary way. So we need to list all products that match a specific category. So this corresponding query, select star from C, where C.category ID equals, say, category A, will return all the products for that category. So, and then, of course, in order to make this single partition, we need to have all the products from the same category sit in the same logical partition. So what that means is that for our product category here, or our product container here, we're going to use category ID as the partition key. So now every time I run that query, it's going to be within partition. So I had another problem here, and that is that every time I query for product set category, I get a category ID and I get a bunch of tag IDs. But what I really want to display is the category name and then a list of tag names for each product as I render that out to the page. So in order to achieve that, I would first need to run my query that I've defined here on the products. I then need to issue a second query on my product categories container just to get the name of the category. And then for each product returned, I would then need to issue a query to product tags to go fetch the corresponding tag names. Now, this could work, but you may be asking yourself, hey, can I just use joins? Well, frankly, you can't. As I mentioned previously, Cosmos is a non-relational data store, and it doesn't support joins across containers. Data that is modeled in this type of data store is optimized such that it can be served in a single request. So to our products table, we're going to add additional properties, including the name of the category, and then also the name for each of the tags that are in there. And so by doing this, we make sure that we can retrieve all the data we eventually are going to need and return that to the client to render on the page and do it in just a single request. Okay, so another demo here. We're going to see what this looks like when we add a category and the tag names into our product container. So let's run this here and go back to. So here's the query I'm going to run. I'm going to query products by category ID here. So get the reference to my database and container. And then here's the category name I'm going to query on. This is components, headsets. And then here's my query. So select star from C, where C category ID equals @category ID. And again, you're going to create your query definition here, passing your partition key. And then we'll loop through the results, and then I'll show a request charge for that. So let's run that one. That's option D here, query products by category ID. And here you can see I've got 1, 2, 3 products. So here's the category ID and category name that came back here. And then the SKU, the name, the description, the price. And then here's an array of tags where I've got the tag ID and the name for each of them in there. So this one's got 3 tags. This one has 2. This one's got 5 in there. And our request charge for that was a little less than 3, 2.91. So that's a pretty efficient query in there. And enter. Go back to, there you go. Okay, let's go back to slides. Okay. Okay. So now when we create a new product, we need to populate these additional properties. But what if we rename a category or a tag? How do we manage that referential integrity between the containers? Well, guess what? In a NoSQL database, you still have to maintain referential integrity between data, right? Data can change, and you need to be able or want to be able to reflect that in other places in there. And it turns out Cosmos actually has a way to handle this. And it's called change feed. Now, change feed is an API that lives within every Cosmos DB container. Actually, technically, it lives within every physical partition, but just kind of ignore that. As far as you're concerned, or users are concerned, you access it through the container reference. So whenever data is written to Cosmos DB, such as an insert or an update, change feed streams these to a delegate that you can listen to and then use that event to respond to data that was changed. Okay, so in our case, we have to listen to changes that occur to our product category container, as well as our product tags container. And every time that data is updated, it will also propagate those changes to the product container accordingly. Okay, so I'm going to do a demo on this. So in this demo, I'm going to show you how to use change feed to do this. First, I'm going to query the product container for a specific category, and then we'll see how many products are in that category. I'll then update that category's name in the product category container, and then we'll show how change feed picks up those changes and then propagates that to every product in the category. All right, so back into here. So let me show you some code. So I'm going to query products for category here, right? So here's my category, accessories, tires, and tubes. And then I'm going to do a count, right, in my product container and pass in that category ID and then do a group by on the category name in there, okay? And then that's the first thing I'm going to run. So let's do that. So query products by category ID. That's option D here. Whoops, wrong one. Oh, that's going to run that. Okay, this is all going to run as a single function. Next thing I want to do is I want to update the product category name. So I have a new thing here, or a new function here, same category name. And what I'm going to do is I'm going to just make a small change. I'm going to replace the word and put an ampersand into the category name. So here I'm creating basically a new category object here, and I'm just changing the name of the category right there. And everything else is going to remain the same category ID. I'm then going to call a function called replace item async. This is functionally an update for Cosmos. And it takes 3 things. It takes the partition key, which, by the way, all of these functions take a partition key. So like the read item async, insert item, and replace item and delete. Yes. And then it's going to take the ID, which is the category here, and then the item itself, right? So that's the updated product category object that I created here. Okay. Next, I want to show you change feed and what that looks like. So here's another little project I have, and it's sitting here running, just listening. And this is the code for change feed in here. So let me walk you through this. So a couple of things you need to know. First is change feed uses this thing we call Lisa's container. It's basically a checkpoint for changes that have been read off the container. So when change feed runs and it polls about every second, it goes to the Lisa's container. It says, hey, tell me the last thing I read in this container. And if it says, okay, you read this and there's a difference between that and what's in there, it'll say, okay, here's some more changes. And it then sends them to the change feed to this delegate that we've called input here. And that's basically going to send it as a read-only collection, and for us, we're casting that or deserializing that to a specific type. The reason it's a collection is because there may be more than one change that's occurred since the last time you read. So it just calls the delegate with this collection full of changes in there, and then you iterate or loop through all those changes and then do something with them. So that's basically, this is kind of the boilerplate for a change feed in here. And what I'm going to do is I'm going to create a new list of task objects here. And then as I for each through every product item or product category item in this collection, I'm going to grab its category ID and its name, right? So this is going to be the new name when this thing comes in. And then I'm just going to add to that task list another function here that's going to update the product category name. So let's look at that. And then I'm just going to go call when all on this, right? Because with change feed, you can process lots of different stuff at the same time. So you just basically set it on a task and let it go. All right, so here below, I've got another function here. This is update product category name. Now, I need to update all the products with that category name. So the first thing I'm going to do is I'm going to write a query, select star from C, where C category ID equals that category ID I've passed in. And then I have another reference to a product container here. So let me go to the top. The very top, I've got two container references. I've got my product category container, which is what I'm listening to here, right? So get change feed processor builder is called off the container that you want to listen to. And then I have another container here. This is my product container. This is the thing I'm going to go do something with. Okay. So down here, I'm going to first do a query against that container because I want to retrieve all of the products for that category. And then I'm going to loop through them all here, right? So just like I was using this for each to loop through to print them out, I'm now going to use it to update the name of the product category for each product that gets returned in my query, right? So, and I'm going to count this too, so you can see how many times it does it. So here I'm going to change in my returned product object here. Category name is going to be the category name that gets passed into the function. And then I'm going to call replace item async, and I'm going to update every product in my collection or in my container with that new category name. Okay. All right. So let's close everything up here. Actually, let's just go back to here. Okay. So here we go. I want you to watch what I do up on top and then watch the change feed down here below because you're going to see it. All right. So update product category name here. That's option E. All right. So here's product category count is 11, and that's the category, accessories, tires, and tubes. Now I'm going to press any key, and I'm going to update that. Now look down below. There, one change received, and I've updated 11 products with the new category name, accessories, tires, ampersand, tubes. Okay, cool, huh? And then I'm going to do another count on that. You can see I still got the same 11 products in there. So everything is consistent, referential integrity maintained. Now let's change it back so you can see it one more time. And here you can see it picked it up right back to accessories, tires, and tubes. And that's it. Okay, let's go back to slides. Any questions, I guess, at this point? I can't tell. All right, well, let me know if there's questions. And hopefully you guys are liking this talk.
Yeah, it's fantastic so far. I haven't seen any questions, but if I see some, I'll stop and I'll let you know. So
maybe people are just, minds are blown and they can't put their hands on their keyboard. So.
I think it's looking really streamlined and really cool. So I'm cool. Definitely enjoying it. So.
I love giving this talk, and I've given it a bunch of times because a lot of customers don't understand these concepts, and it's absolutely critical to be successful on this using this database or this type of database. Understanding the concepts and the techniques for modeling data is the only way to get what you need out of this thing. I mean, the promise for a NoSQL distributed database is functionally you can get theoretically unlimited scale, right? And it's a scale out database. So you just keep adding servers to it. In a relational world, like a SQL server, there's a limit. There's a 4 terabyte limit for an unsharded database in SQL, right? By the way, sharding is just the same exact thing, right? We call it partitioning, but it's a scale out, right? And then you have to figure out which data goes on which shard or partition. We're doing that already here, right? We try to make it as simple as possible by saying, pick a property in your data and use that to distribute your data to these different physical partitions or shards within there, right? And because it's distributed out like that, accessing that data is always going to be fast if you're doing something like a point read, right? Because it's just, you need to know the partition key so I know the address of that server so I can go get it. So that, we're unique in the fact that we're the only database in Azure that has an SLA on latency. So for a read or a write of a kilobyte of data or less, using our direct mode API, using our SQL API, we have a SLA of less than 10 milliseconds at P99. So 99 out of every 100 requests we guarantee are going to be less than 10 milliseconds. And the P50 of that is generally about 4 or 5 milliseconds. So it's generally quite fast. And that's true whether or not your database is a megabyte in size or a petabyte in size. It doesn't matter because we're scale out, right? Your data is spread out amongst all these different servers. You provide the partition key and the ID to get your data, and we'll get it for you and return it in less than 10 milliseconds. So, okay.
I just wanted to say, I think it's really cool how you have the metrics in there as well. I mean, theoretically, I understand that, it would be very quick at doing those things, but, kind of proving it is definitely a great thing to do as well.
Yep, absolutely. In fact, this is what we tell customers is they need to prove this out. When they go from dev, test to prod, you need to put serious load on your database because you need to know if it's actually truly going to scale. Right? This is the trap. So people that don't understand these concepts in modeling and partitioning, they go and they dev test their thing, they go into prod, and then a month, 6 months, a year later, they realize that they made a poor choice. And the problem is that you can't go back and change the partition key because it's actually physically assigning data to where it's physically stored. So you need to go and create a new container, pick a better partition key, hopefully, and then copy your data from one container to the other and then switch it over. It can be very painful for customers. So having this knowledge up front makes you a winner in the end. So, okay, let's move on to our last set of entities here with the sales order. Do the same exact thing here. We're going to create JSON documents out of these guys. And of course, this is also a good candidate for embedding because it's a one-to-few relationship, right? You're not going to have a sales order with a billion items in there unless you're, unless you're crazy and can't stop buying. Next, stored in its own container, we'll call that sales order. And let's look again at the operations because we need to decide on a partition key here. So of course, we need to create a sales order. And then we need to list all sales orders for a customer in here. So that's what this query looks like here. We're going to select star from C where C.customer ID equals customer A. So if we partition by customer ID here, this would make it a single partition query, which is good. I think that makes sense, right? So this would be quite a frequently run operation, listing all the sales orders for your customer within there. It doesn't impact creating a sales order, and there that kind of makes sense as well. So I think for this thing here, we're going to use customer ID as our partition key here. Okay, before we go any further, I want to take a step back. When looking at the containers we've designed so far, it's interesting to note that we already have a container that's partitioned by the customer's ID, and that's the customer container itself. So could we store, say, the customer record and the sales orders in the same container? Yes, absolutely, we can do that. Not only is this technically possible in a database like Cosmos DB, this is actually a best practice for this type of database. Cosmos is schema agnostic, right? It's a NoSQL database, so it does not enforce schema at the database level. So this is something that's totally supported. And it's also quite suitable when data shares similar access patterns and, of course, shares the partition key. And that's true here as well. Customer is going to the customer is going to log in, so you're going to access the customer data. And then, of course, the customer is going to access their sales orders or create new sales orders. So in the case here, it makes sense to store these things in the same collection. So what we'll do is instead of storing these in different containers, we're going to store everything in a customer container here. Now, I've got to make some other changes here as well. I'm going to change the partition key from ID to customer ID, and then I'm going to add customer ID to the customer object or the customer document itself. So now the customer document is going to have the same value for the ID as it does for its customer ID as the new partition key property. Another thing I need to do is I need a way to be able to distinguish between a sales order and a customer within the container. So I'm going to add what we call a discriminator property, or this type property, and I'm going to give it a value of customer or sales order for each of those different entities. And this will allow me to query for them individually if I want here. Okay, so now what we have is a customer's container where each logical partition will contain exactly one customer row and then all of that customer's sales orders within here. And so now to get all the sales orders for a customer, I just simply run with this updated query here. So this is select star from C, where C customer ID equals customer A, and C type equals sales order. Okay, so let's go back into our code and we'll take a look at that.
We have a quick question here if you're available to take one.
Sure.
Says, why would you use Cosmos DB for a well-structured data like your schema as opposed to using something like Azure SQL?
Well, for a number of reasons. One, speed is one. So we're the only database that provides latency SLA. We're also the only database that has 5 nines of availability. And that is because we're distributed in that we run in every single region. So we can survive regional outages with a very low RPO, in fact, a minimum RPO of 5 minutes. Or you can have an RPO of 0 if you want to run strong consistency. However, you're going to pay for that in terms of latency on your writes, because every time you write data, it then needs to write to every region that you have your account set up. You can also get an RTO of 0 with a higher RPO if you want to run multi-master or active-active. We call it multi-region writes. And what that does is that every region that you provision is now a writable endpoint, rather than just having a single region write, where you're basically primarily writing in a single region and then you replicate to a secondary region where you either do reads or you use it for failover, for HADR. This is good in a couple of ways. One, not only do you get RTO 0, because what happens is that if the primary region stops responding, the SDK client will automatically redirect the request to a secondary region. And it does it within 30 seconds, and frankly, it probably does it even faster than that. So you have 0 downtime, or RTO 0, with that. Other reasons you would use it as well, I mean, just because your data may not be structured doesn't mean that this is a bad, or this is a database that you couldn't use it. There's plenty of customers that have very structured data, but they have higher requirements for the latency, the availability, those sorts of things. So that's, I think, one of the primary reasons that we see customers using it. I mean, consider that Cosmos was born in Azure, right? I mean, SQL as a database has been around since 1970. So it's 51 years old now. Now, granted, back then when SQL was created, the cost of a megabyte of storage was like $100,000 or something like that, right? Now storage is cheap. I mean, I got a terabyte of storage on my phone, and that just cost me a few $100. What's really expensive now is the cost of compute relative to storage. It's very expensive. And Cosmos, being a relatively new database, it's only been around since 2015, 2016, is that it's as a NoSQL database designed to optimize around request, or the compute end of it, which is why a database like Cosmos is fine with duplicating data in your account, because the cost of storage fundamentally is cheap in there. What we want to do is design our database such that it serves data exactly as it's needed by your application with as minimal changes to it as possible. So you want to optimize around the request with a database like Cosmos, and you do that by taking advantage of the fact that it's schemaless or schema agnostic. You have schema, right? Like if I go into my class here, models, here's my schema for my database, right? I've got a customer object, customer address, location object, password, product, right? This is where you enforce your schema, is you do it at the application level. And this, of course, gives you flexibility that if you want to change it, you certainly can within there. With something like SQL database, you're going to have downtime as you go and do alter table and add additional properties to it. So there's lots of reasons. There's no one reason, but you don't need to have unstructured data to use a database like Cosmos. Like I said, if you have insane or needs around availability or latency or something else, this is also a good choice. Okay, any more questions?
That's the only one. Yeah, that's pretty good. I could see where you'd have that massive performance gain, and of course weighing the cost of the storage versus the compute. So yeah, it definitely makes sense.
And the other thing too is it's conscious to not have kind of enforced relational constraints, right? We want to be write optimized so that there's nothing blocking when you're trying to write data to the database within there. So we physically could enforce relational constraints across physical partitions, but here's the problem: is that if say a physical partition went down, and by the way, there's 4 physical partitions for every time you write data. We store data in 4 different replicas in 4 different pieces of compute. So we keep multiple copies of your data for availability, because if one of those replicas goes down, you still got 3 more. And every time you do a write into Cosmos, you write into 3 replicas, and then it copies over to the 4th one. So that's just additional bulletproofing, if you will, within region, right? So forget about replicating to another region where we do the same thing again. Every time you write data into Cosmos, it's stored 4 different times, okay? And then that just gives you additional availability. So what I'm saying is that if you had to enforce relational constraints across physical servers and one of those servers failed, well, then your availability all up is gone in that sense. So it's a conscious decision to not enforce that type of thing. But like I'm showing, like maintain referential integrity, you can totally do it. You just need to know what kind of technologies to use and techniques around that. So, okay, let's keep going. I'm getting close to the end here. Finally, I want to look at this last request we need to serve. So what we want to do is we want to query our top 10 customers by the number of sales orders they've got. So this request requires you have to count the number of sales orders for each customer and then sort those in descending order, then return the first 10 that come back out of that. Now, even though customers and sales orders sit in the same logical partition, this isn't actually a query I could do with Cosmos DB, at least today. So again, what we're going to do is we're going to denormalize. But in this case, we're going to denormalize an aggregate. And we're going to store that in the customer entity within our customer container. So I've got this new property here, sales order count, and I'm going to store it in there. So what we want to achieve is that every time I add a new sales order into my customer container, I'm going to increment this sales order count on my customer object. And here we can benefit from the fact that because customers and sales orders sit in the same logical partition, we can use transactions actually. So Cosmos does support transaction, which is a very relational concept, because the data sits in the same logical partition. So remember, it's a conscious decision not to do these types of relational constraints across partitions, but because it's in the same partition, we don't have the same issues with regards to loss of availability or other kinds of weirdness that can happen when you're trying to do these kind of distributed transactions across these different pieces of compute. And so we can do this in a transaction. Now in Cosmos, you could do transactions one of 2 ways. You can use a stored procedure, which is written in JavaScript, and I'm not a huge fan of that. But we also have a way to support this through our SDKs in both the Java and C and .NET SDK using this feature called transactional batch. Okay, so now what I can do is I can write a query that looks like this. So I'm going to select top 10 from C, where C.type equals customer, and then I'm going to do order by on my sales order count in descending order. Okay, so in this demo, let me show you how all this works. And I'll close you. All right, so I'm going to query my customer and sales order ID. I'm going to call this function here first. All right, and I got my customer ID here. This is the same one I was querying earlier. And then notice in here, in my query, I'm not using the type property. So I'm going to get back the customer record, and I'm going to get back all their sales orders too, which is another really kind of kind of a cool, tricky thing is I can get two different types of entities with a single query and pass that back to my client. So again, really focused around optimizing how you model your data can have a huge impact in how efficient you can get with your applications. Now, before I was deserializing these queries into specific classes. Because I'm mixing them here, I can't do that. I have to use dynamic type when I deserialize this data because I'm getting different types of objects in here. So the rest of this all looks the same, right? And then I've got a customer object here, and then I'm going to create a list of sales orders. And then as I iterate through each of the results here, I'm going to, for each of this thing, I'm going to inspect the type property. And if it's a type customer, then I'll deserialize that into a customer object here. And if it's type sales order, I'm going to do orders.add and then deserialize it into that there. Okay, and then I'm going to print this out. So query for customer and all orders here. Okay, so I've got product here, product here, product here, and here you can see sales order count. Has this thing been sitting in here for a while? Oh, I got to get rid of that. Here, let me fix this something. I didn't clean myself up here. That order's been sitting there a while. Okay, so let me query for the customer and all their orders. That's number G here. Okay, so I've got a product here, and then what I'm supposed to show you is sales order count of 2 right here. Okay, so there's my denormalized aggregate that I've got. So that's that query. Now I'm going to create a new order and update the customer item total. So let me show you that code here. Let me get this back to normal. Okay, so here's my customer here. Now the first thing I'm going to do is I need to fetch my customer. And I'm going to do that using my point read that I showed earlier, right? So I'm going to pass the ID is the customer ID, and then the partition key is the customer ID. Remember before we created a new property, customer ID, that's our partition key. But for the customer record, it's the ID, right? So I don't need to specify something here. I know exactly that ID is that same as the partition key within there. And I'm going to save that into my customer object or deserialize that out of the response object here. And then I'm going to increment sales order count right here. Okay, so just sales order count plus plus. Now I'm going to create a new dummy order here. So I've got a GUID. I normally use new GUID here. And then here's a new sales order. So I need to create sales order, and I need to specify the type, right? Because I need that discriminator property. Pass in my customer ID. I got an order date, and then of course a blank ship date because we haven't shipped it yet. And then I'll add a couple of products in here. I've got a new mountain bike frame that's black and 38 inches, I guess, and then some racing socks as well to complete my order here. And then below that, I'm going to use this thing called transactional batch. So this comes off the container object here, and I'm going to call create transactional batch. And because transactions happen within a single logical partition, I have to pass in my partition key. And that here, of course, is going to be our customer ID. And then I'm going to call a couple of functions here. I'm going to call create item, and then I'm going to pass the sales order we just created above. And then I'm going to call replace item, which is the update. And I'm going to pass in my customer ID and then the customer object in there, and then call execute async. Okay, so here we're going to create new order and update order total. That's option H here, and all successful. Now I'm going to query for my customer and all their orders. So option G, and here's my new sales order made just now with my new HL mountain bike frame that's black, and then a pair of racing socks. And if I scroll up, here you go, sales order count is 3. Okay, so awesome sauce. And just like creating orders, you can do that in a transaction. You can also delete an order and also do that in a transaction. So here I've got my customer ID and order ID. I'm going to call read item async on my customer object, and then I'm going to decrement sales order count to down 1. And then I'll call transaction batch again. And this time I'm going to call delete item and just pass in the order ID, and then replace item on the customer object again. And then it'll update the customer within there. So go ahead and I'm going to delete an order here, that same order. Now, if I go back and query for my customer and all their orders, and as you saw this before, I did this because I wasn't ready. And then here you can see that new order is gone, and my sales order count is now updated to 2. Okay, so I showed you a whole bunch of stuff here. And the reason is because I needed to do this so I could run my top 10 customer query. So here's my function for that. And here's my query. Select top 10, first name, last name, sales order count from my container here, customer, where C type equals customer, right? Because I have to distinguish that. I'm not pulling sales orders in there. And then do an order by on sales order count in descending order. And then I'm just going to print all that out. And we'll run you. And this will take a second to run. And here you go. So we got Dalton, Mason, Henry, Samantha. All 10 of these guys are going to get a special discount or I don't know what, gift card. And here you can see our request charge of 13.08 RU. Okay, so let's go back to slides here. So I don't know if you noticed, but that last query was actually a cross-partition query, right? Because what's the partition key of our customer container is customer ID. And here we were running a query that went across customers. So I know before I said you should try to avoid these, but in reality, it's kind of hard to avoid them for every different situation. And in scenarios where you're just going to run it, say, once a month or something like that, it's okay. It's okay for operations that aren't run very frequently. It's when they're high concurrency queries, you want to avoid that type of thing. At some point, and also, of course, if they're in small containers as well, at some point, it may make sense that a cross-partition query that was once okay has gotten to a point where it's gotten too expensive to run. This can happen when you get into containers that are maybe thousands of partitions in size. In that case, what you want to do is you want to denormalize that aggregate. Basically, you're creating a materialized view of that data, and you're going to store that in another container. So what would happen is you don't create that in terms of transaction there. You're basically going to create an upsert statement, and it's going to upsert the value for that sales order count into another collection, and then you run the query and you use that collection or container, to serve that query that you then run. The materialized view pattern is another very frequently used operation or type of trick where you're essentially, and it's just like the name explains, right? And it's for anybody that uses SQL, and what a materialized view is easy to understand. In this case here, we're basically materializing an aggregate and then using that to serve queries. And this is common in workloads where you have, say, high write throughput and high read throughput. And this is also another thing that's not uncommon is customers are often kind of frozen by the fact that they may need to have, or they may need to optimize around different partition key values. It's quite common that data gets written into one container and then they use change fee to write it into another container with a completely different partition key. And that each of the containers kind of serves different purposes or maybe serves different queries. It takes a little bit of math and figuring to get to knowing whether you need to do that. But that's why, again, understanding the operations that you're running and the concurrency of those operations is so important to being able to do a good design, a scalable design for a database like Cosmos DB. So, okay. Our final design here, we've got a customer container with customers and sales orders. I got a product container here with my products, and I got a product tag container with tags and a category container with categories. There's one more optimization we can actually do here, and that is I can create another container, and we'll call it product meta, because they're both use type as a partition key with their own unique values. So this is another way you can optimize data like this and just store it in a single container, because it only needs every container, unless you're using shared throughput, but every container needs its own throughput. But if I store it in the same container, I can do that. And this is actually a best practice for master data, right, or reference data. Is just store it all in the same container, and then use the type of data as its partition key. Because you're never going to run into 20 gigs of product categories or 20 gigs of product tags. And if you do, you can also you can use a composite key to get a higher level of cardinality within there, so that you can easily keep that data within your 20 gigs. So here's our final design. Our 3 containers from 9 original relational tables that we had from AdventureWorks. And this database will scale and perform to essentially petabytes in size, unlimited size within our application. So that's it for my talk. Everything you saw here is available on GitHub. So you go to github.com/AzureCosmosDB/CosmicWorks. All the code I showed is there. Actually, all the data is there as well. I am working on writing a data loader. It's actually written. I just haven't merged it into this repo. But you can take a look at this and look at all the code in there and look at the data and get it set up. I've got an ARM template in there that'll set it up. You can also run a CLI bash script I wrote in there as well that'll also set it up for you. There's a good article, Practical Cosmos DB. This is basically showing modeling and partitioning using, like, say, a WordPress or a blog platform. Lots of great videos on YouTube. And then, of course, we've got a little microsite called Got Cosmos that I run. And on there, we've got a weekly podcast that I host every Thursday at 1 p.m. Pacific, which I think you guys are Central. So what would that be, like 2 p.m., I guess, for you guys in Austin?
That'd be 3 p.m. for us.
Oh, is it? Are you guys 2 hours difference? Okay.
Or 2 hours, yep.
Okay. So here's gotcosmos.com/TV. You can come see me every week if I didn't burn you out watching me now. Lots of great stuff. Next week, we're going to recap all of our build announcements. We got a lot of cool stuff coming for build. We always do. And then just more great episodes coming up. You can check that out as well. We just ran our own first Cosmos DB conf. This is kind of like a .NET conf, but much lower level. That guy, the .NET conf runs like 3-4 days or something like that, nonstop. We can't quite do that yet. But lots of sessions in here. There's live sessions you can go and see in here. Keynote. There's some really great content in here. Lots of good on-demand sessions in here as well. So come and check that out. Here's the repo with all the stuff in here. And you can come and check that out as well. It's even got a deploy to Azure thing in there as well. So any questions from anyone? Let's see. I see why. Okay, that you asked that one earlier from Albert. Yeah. Okay.
The only question I might have is kind of are there security benefits? Because I know it's not strictly relational, but you demonstrated that you could use it relationally.
Security benefits. So let me talk about security. So the way we use these master keys in our SDK to access Cosmos DB. So you secure the database using a pair of master keys. There's a rewrite and a read only. We just recently announced support for Azure AD and RBAC. So now what you can do is you can actually authenticate using the service principal ID from an AAD token, and then pass that when you do create a new Cosmos client using our SDK. And you can get all the RBAC goodness out of that as well. So I can actually now go and create AAD groups and then give them permissions using the new RBAC model, like read from this container, write to this container, I can query this, do that. And then that's all going to be managed basically like you would like a SQL database in terms of kind of its having that AAD support, where you basically single auth into your app using your AAD identity, and then getting all the RBAC goodness out of there as well. We also, of course, and I just actually on my podcast today just did an episode on network security, but we also have support for IP firewall, so you can secure the database and just limit it to a handful or a cited range of IP addresses. We have support for service endpoints. So you can restrict access to people on a subnet or a VNet or a subnet within there. And we also support private endpoint, which essentially removes the public IP address, right? Because Cosmos is on the public internet, right? It's the endpoint is out there. The URI for your endpoint, your my account.documents.azure.com resolves to a public IP address. So you can use private endpoints to remove that, and then you basically get a 10 dot address, and you connect to that, or it resolves to that, right? So, and that's basically using also the private DNS as well, because you need to have a way to resolve that FQDN so that you can access that 10 dot address in there. So lots of options for security, of course, in there, and authentication. So we got your auth-z and your auth-n covered from the network all the way down to the app. What else? Customer managed keys. So I guess we're in the security realm. You can encrypt your data as well. I mean, we already encrypt it using a Microsoft managed key. If you want to encrypt it again, you can go and create a key, store it in Key Vault, pass that key URI, the resource URI for the key and Key Vault to us, and you put it in your database account, and then we will encrypt your data again on there. So, and then at Build, we've got some cool announcements coming up around security, but I'm not going to.
No spoilers.
No, sorry. No spoilers here. So I got to.
Fair enough.
Yeah, keep my job.
Well, I'll be excited to see what's coming up there.
Yeah, definitely. Come check us out. I mean, that's Build for us is the big event because, Cosmos is a developer's database, right? You don't find SQL is, big in the DBA community because you need DBAs to run it. Cosmos is fully managed. And the only way to access it really is, you have Portal, but you don't really use Portal to do much of anything, just other than just getting things kind of started. All the work happens when you're writing code using our SDK to read and write data in and out of your database, right? So it's very developer focused, very developer friendly in there. So we're kind of a different database, if you will, from the others.
Excellent.
Yep.
Is there anything else you wanted to add, or is that?
That's it, really, for me. So unless you guys got any more questions.
No, I guess we'll call it a show. Thank you very much, Mark, for coming out. You really highlighted some great strengths and some great reasons why you would make the decision. Make the informed decision to go with Cosmos DB and really why you would consider it versus some alternatives. So,
well, what I want you to walk away with is, use the right database for the job. You can't use Cosmos. It doesn't make sense in every scenario, although you can use it for a lot of different workloads. But being smart about how do you use the database, how do you model, how do you design for it? Why is it built the way it is? There's a reason why Cosmos is built like this, and it's to give you that basically unlimited scalability in there and just insane fast performance. But you can't get the promise unless you understand the concepts and design for it. And that's what I hope that you all got today. So
I definitely feel that's the takeaway I get, and I'm pretty new to NoSQL, so that's mission accomplished.
Yep, cool. Well, follow us on Twitter at Azure Cosmos DB. I'm on Twitter all day as well. In fact, I monitor our Twitter account. So if you got questions, you can ask them on Twitter. I'm also quite frequently on Stack Overflow, pretty much answering questions there, and on our Microsoft Q&A. So my job is to try and help developers be successful on Cosmos. That's kind of my other job too.
Perfect. Well, it was a great demo, a great presentation. So we appreciate you gracing us with your knowledge and your presence here with the San Antonio group, and I'm sure with the .NET group as well. So
great.
Okay, we'll wrap it up. Thank you very much, everybody, for coming out. We appreciate it, and please join us next time.